Fun world we live in. All right, we are going to pass out the quizzes first. Not a quiz, the quizzes from last time. I have these quizzes folded so that you can't see the grades. And so your grade is on the back side of it in the corner. And then also you probably know what your grade is if you looked online. So please grab yours, pass the stack around. And then I'm also going to pass around that sheet for the related rates. Remember I told you had like a worksheet? Take maybe 3 or 4 of these copies, and there's front, oh wait, it's supposed to be front and back. It's not. Okay, take 4 or 5 copies for yourself and then pass the stack around, please. All right. Let's start class. Let's just jump right in. We're going to do more. Oh, do you have a question?
Are we going to use these sheets for the examples today, or is it just so
You can use them for today. Yeah. Remember, you have access to these, right? So you can print some more copies for yourself if you want. Remember, I said on the test, the next test, bring your own if you want to use it. All right. So let's do an example here. We're going to do more related rate problems. Couple of more, and then we're going to move on to the next chapter. Yes? Yes, you could bring a couple of copies of it. Oh, and I should tell you how I like to do the related rates on my exams, because students love them so much. What I normally do with the related rates is I give you 4 or 5 problems and make you choose 2 or 3. And that way, if you look at one, you're like, I have no idea how to get this thing set up. Hopefully, one of the other ones you feel more comfortable with. So it's not going to be one problem you have to do. It's you choose from a few. And you are not allowed to do all of them for extra credit. Okay, that's part of the give and take. I give you an option, but you have to choose however many I tell you to choose. All right, so let's look at this, this problem here. A conical cup is 4 inches tall, 6 inches wide. So we need to first understand what I mean by a conical cup here. I did not include a picture, but what I mean is something like this. You know those little those little paper cups that they put on the igloo, you get a little drink of water now? Anyone ever play sports? Yeah. So you got this little conical cup like this, right? And we are told that it is 4 inches tall, 4 inches, and it's 6 inches wide at the top, all right? And it comes down to a point. And then we're told that water is being poured into this cone at a constant rate of 2 pi, so 2 pi is just some number, 6 point something, right? 6 and some change, cubic inches per second. Per second. A second per second, yeah. How fast is the water level rising when the water is 1 inch from the top of the cup? So you have to see if you can visualize. You've got this cup, this is fixed, nothing's moving here, but we're pouring and water is coming up, right? So we got this water level in here. Right, that's some water, water's being poured in, right? And that's kind of, I think, the best I can do with my picture. I want to know how fast the water level is rising, right? How fast the water level is rising. So I'm going to label the water level here, right here, from here to here. I'm going to label that H, because I really want to know how fast that H is changing. So I should label it in my picture. And this is starting to look like this is going to be my general picture, meaning that things are changing, right? Things are actually moving here. The water level, I'm imagining, is coming up in that picture. Are there more? Okay, I've got plenty more of these. Do you want a couple more and pass them back around? Yeah? Take two or 3 more? Oh, you didn't get them. Okay, sorry. There we go. Take 5 of them. All right, so that's my general picture. Let me draw the picture at the instant in time that we're talking about. At the instant we're talking about, we have our conical cup That doesn't change. This is 6 inches. This is 4 inches. But here, my water level is what? At the instant we're talking about. 1 inch from the top, right? 1 inch from the top. It means my water level is up here somewhere. And if it's 1 inch from the top, then how deep is it? The whole cone is what? 4 high? So it should only be 3 high, right? So in this particular case, 1 inch from the top means that my H here is 3 inches. See, I have to kind of like work backwards. I know how far it is from the top, so that means the height has to be 3. Are we all good with this so far? All right, let's start writing down some things. Things I'm given, maybe what I want. I'll have some equation. All right, what am I given? The rate the water's coming in, right? That's the rate the volume is changing, right? This measurement, 2 pi cubic inches a second, is a rate of change in the volume. So I'm going to say that I'm given dV dt to be 2 pi cubic inches per second, like that. That's enough. Was that you last time too? Did I told? No? Okay. You had the hiccups last time, right? Okay. All right, what do we want? What do we want?
How fast the water is rising.
Okay, we want to know how fast the water level is rising, right? Which is for us what?
Height.
The change in the height, right? dH dt. We want to know dH dt. At 1 inch from the top, but for us that really means H is 3, right? Every time you write down, well, not every time, some problems this doesn't matter, but most of the time when you write down what you want, there's also going to be the moment that you want it, all right? I think that's everything I need.
The equation and the implicit.
Yeah, I need an equation, right? I have to have an equation now, and this equation must relate the height to the volume. Now, be extremely careful here. The equation I'm looking for must connect the height of the water, right, to the volume of the water. Not the cup, the water, right? The water has a volume and the water has a height. That's the thing I need to connect. So I need to see if I somewhere have a formula for the volume of a, the water part is still a cone, isn't it?
Yeah.
Okay, so I'm going to draw a picture here. I have just, this is the water, not the actual cone. It has a certain height, doesn't it? And would you agree that that also has some certain radius, I'll call R? Now, is that radius 3? No, it depends on where the water is, right? So I cannot put 3 there. It's just R. And you look in your formula sheets and you find a formula there and it says what? 1/3 pi r squared h. 1/3 pi r squared h. That is the volume of this cone of water that's inside the cup. I am trying to connect H and V together. Have I connected H and V together?
Yes.
Yes, but there's a problem.
R.
I have R. And if I differentiate this right now, right? If I take the derivative of this right now with respect to time on both sides, I know I'm going to get a dV dt to come out, which is actually good. I know that I will get a dH dt to come out somewhere, which is good. But I will also get a what? dr dt. And I don't know anything about dr dt, do I? Right. Well, we don't know. See, we have to be looking at the general picture. The water level's here, so we can't say anything like it's 6 or 4. We can't fix anything, right? Is there a question or no? Okay. So do you all understand that my volume formula has one additional variable that I don't want to have there? Yes? That's a major problem. So I've got to somehow find a way to write this formula where the R is gone, where the R isn't there. So I'm going to have to be extremely clever, right? So here I go. This is a classic problem, all right? If it's one of those problems where you just kind of have to see it done, and then you go, oh, okay, maybe I wouldn't have thought of that, but now I know maybe I can think that way. So imagine that this is frozen, not here, but just imagine this water's like frozen in here, and we were to slice this cone right down the middle and open it up and look at it from like a cross section. Here's what I would see. I would see a big triangle, right, like this. And then inside of that would be the water level, which would be somewhere, right, like this. I'm going to do it as a straight line. Y'all see that? Now, let's just look at one side of this. So I want you to imagine cutting this down the middle. And we're going to look at just, let's say, the right side of that. So if I look at just the right side, can you tell me at all how long this is from here to here? That's 3, right? That's the cone, the cup, right? So that's not changing. Do you know the distance? That's from here to here. Do you know the distance from here all the way down? 4. That's not going to change either, right? Now, in terms of the water, the distance from here to here, we are calling that what? H. And the distance from here to here, we are calling what? R, right? Now, why did I do that? I did that because I have, in that picture, similar triangles. I have 2 triangles. I have a big triangle and a small triangle. Let me draw the 2 triangles. I have the big triangle, which looks like this. This is 4 and this is 3. This is a right triangle because I dropped that line, the green line, right down the middle, right? And then I have this smaller triangle that's inside of it, right? That looks like this. And that's R and that's H. And the most important part of this is that they both share this angle right there. That angle is the same for both triangles, right? So if this angle is the same as that angle, and these are both 90-degree angles, then that means this must be the same as this. And therefore, they are similar triangles. And we did one problem like this last time, right? Was the street light pole and the person walking, right? Or trotting, whatever we said. So I have similar triangles, so what I can do is I can set up a ratio of the sides any way I want. So here's what I'll do. I'm going to do it, like I said, any way that I want to do it. I'm going to do this divided by that. R over 3 must equal this divided by that. So H over 4. And what's nice about this relationship is that this gives me a connection between R and H, right? And if I solve this for R, let's do that. If I solve for R, I'm going to just multiply both sides by 3, which would give me 3H over 4, or 3/4 H. Then do you agree that I could take this value of R, which is now in terms of H, and plug it in here, and I would no longer have R's. I would have H's everywhere. That's what I'm going to do. Yes?
Why couldn't you just use like a numerical number for R?
Because the R is the radius of the water, right? And as you pour water in, the water level comes up and that radius is changing, isn't it?
Yeah.
So it's not fixed. If you fix anything, then you can't do calculus anymore because everything's frozen in time. It was that thing, like I said, if I'm like this, how fast am I going? Well, I'm not. You have to allow everything to be a variable before you can fix anything.
Is that why H wouldn't be 3?
That's why H wouldn't be 3. Exactly. That's why H wouldn't be 3. Now, H can be 3 here, right? But remember, this we can only look at this picture after we've taken the derivative. All right. Any other questions?
And then if it was like different, you could do 3 over R.
Yeah.
4 over H. You could like swap it
I
out.
could have done 3 over R equals 4 over H. The reason I didn't do, H. The reason I didn't do this is because now my R and my H are on the bottom.
Yeah.
And I prefer to have them up top so I can solve for them easier. But you could also just cross multiply and then still get r by itself. All right, so here we go. I'm going to go back. We're still trying to get the equation, right? We're still trying to get the equation. I'm going to go back to that equation. I'm running out of room. Try and squeeze it in right here. So I'm going to go back to my volume equation. My volume is 1/3 pi, but the radius I just said was 9h over 4. That radius squared times h. 1/3.
You said 9H.
You say yeah. You said
Oh, I already squared it, I guess. I'm sorry. 1/3 pi times 3h over 4. That quantity is going to be squared, and then times h. See, that formula no longer has r. Now I'm going to clean it up before I actually differentiate it. I'm going to clean it up. I am going to now square the top and bottom, so that's 9h squared over 16, and then I still have an h over here. I'll come back to this. Let's see, this 9, 3 goes into that, right? It's about all I can do, I think. So my volume will be, I have a 3 and I have a 16 on the bottom. I still have the pi, and then h what? Cubed, right? H squared times h cubed. There we go. That's my equation.
the h on top?
Pardon?
Because of the h, right? Because you're multiplying.
Yeah, this is like h over 1. So it just goes across top. All right?
Oh, the one, oh, yeah.
I just reduced 9 divided by 3 and got 3 on top. All right, there it is. I have an equation. This equation is only valid for this particular situation, right? That's not the volume of any cone. That's the volume of this cone. That's the relationship that we have. So now I'm ready to differentiate. So implicit, right? Implicit differentiation. I'm differentiating with respect to time. So the derivative with respect to time of the left side, v, equals the derivative with respect to time of the right side, 3/16 pi times h cubed. What is the left side? dv dt, right? dv dt. And dv dt is the change in volume with respect to time, which is actually given to me in the problem to be 2 pi. So I like seeing that here. Over here, Umberto, we have a constant, right, in front of a function. And so I'm going to take the derivative, right? So what I'm going to do is bring the constant for the ride. And now I'm going to take derivative of h cubed, which will be what? 3h squared. But then I have to do chain rule, right? Times now the derivative of the h with respect to time. Now, I didn't show the details on this. I'm hoping now that we're on the 3rd day of implicit, that everyone's comfortable with the idea that of differentiating with this with respect to t gives you this. And I'm just going to do a quick check to make sure I have everything I'm looking for here. dv dt is what I'm given that, right? Do I know h? Well, now I can fix everything, right? Now I've taken the derivative, so now I can look at the instant. Do we know h at the instant? 3, right? It's also right here, 3. So that we know, and dh dt is what we're solving for, right? So I'm happy to see that. I've got everything. So I'm going to put the work over here. All right, plugging in. The left side is dv dt, which is given to me to be 2 pi. That must equal 3/16 pi times 3 again, times h, which was 3 again, squared times dh dt. Here we go. So all I did was replace the dv dt with 2 pi and replace the h with 3.
Are we solving for dh?
We are solving for dh dt now. Yep.
So 9 times
3 times 3 times 3 times 3, that should be 81. We should get 81 on top. So 2 pi equals 81 pi over 16 dh dt. times dH dt. And then, yeah, right now, this is something I see real quick. I could just divide both sides by pi. That's real nice because the pi will go away, right? Divide both sides by pi. And then multiply both sides by the reciprocal, right? Just multiply this by 16 over 81. Do the same thing over here, 16 over 81. The 16s cancel, the 81s cancel. And so the right side is dH dt. And the left side is 32 over 81. And we could get that as a decimal. Did you do a decimal or no?
No.
No, okay, I thought that's
was
what you
just
did.
multiplying with 16 and 2.
Can someone do that real quick as a decimal? What is that approximately? What is it? Is it exactly? Is it 0.39, 0.39-ish, somewhere around there is approximately dH dt. Okay, what are the units of this here? Height over time. Height in this problem was measured in inches. Time was in seconds, so this is inches per second. So we've got this cone, right? 4 inches tall, 6 inches wide at the top. We're pouring in water at 2 pi cubic inches per second. At the exact moment, the height of the water is 3 inches high, right? At that moment, the water level is coming up at 0.39 inches per second. So here's a visual animation of what's going on. Imagine you've got this empty cone, right? There's our empty cone. And we're going to start filling it, right? Maybe I should have shown you all this in the beginning, but I was trying to do it without any visual aids because during a test you won't have anything but a picture. At the most you'll have is a picture. So there's my cone, right? And now I start pouring water into it. Think about the height of the water. The height of the water is going to start coming up, right? In the beginning, is it going to be coming up fast or slow? Fast. And then as it gets higher, is it going to be coming up as fast, or is it going to speed up, slow down? What do you think? Should slow down. As long as I'm pouring at a constant rate, initially it should come up fast, but because it spreads out, it's going to take longer for it to come up more. So we are saying for a problem like this, here I'm pouring water in. See how in the beginning it was kind of fast? And then the more time goes on, it's taking longer for it to come up. So at the exact moment that it's 3 inches, whenever that was, I can tell you how fast it was coming up. It was coming up at 0.39 inches per second. Remember that at any other point in time, it's going to have a different speed, right? It's going to have a different speed at which it's coming up. If you ask, hey, how about when it's 2 inches high? You'll have a different answer. If you say when it's 3.8 inches high, you're going to have a different answer. Okay?
And we knew that the height was 3 of the water because it said when it's 1 inch from the top.
Yes. The 1 inch from the top is why we knew we were talking about 3 inches high. Because remember, the cup was only 4 inches, so an inch from the top would mean that the water height was 3. All right, that's a classic Cal 1 problem for related rates. I want to do one more, at least one more. All right, we have a little video to watch. Let's see if the audio comes out or not. Let me back this up. I don't want to watch the whole thing.
Valves.
Whoa,
Intake
whoa,
and
whoa, 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 whoa. Sorry. Wasn't sure if the volume was turned on over there, but I guess it is.
exhaust, a fuel injector, spark plug. A four-stroke engine
Holy
is called
shit.
a
Okay.
four-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward compressing the air and fuel to make a highly combustible mixture. This is
All right, so what we're looking at here is the way an engine in your car works, right? Some of y'all are aware, some of y'all have no idea, right? So what I want you to see here is that what's happening, and this is what the gentleman is saying, sounds like a 1970s training video to me, like way back in the day. Basically what happens is you first put a bunch of gas and air in here, all right? This comes down, the gas and air go in here. Then the piston comes back up. There's compression, there's a spark, it blows up, ignites the fuel, it pushes the piston back down, and then it comes back up and pushes all the exhaust out. And that comes out your tailpipe, right? So this just is happening. There's four actual strokes for this procedure to complete one cycle.
It's called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion.
Look what's happening here.
gas mixture. This is the combustion stroke.
Piston comes down. There's a rod connected to this
As the piston
crank.
travels downward, the exhaust
Here it is right here. It comes up.
the burned air fuel mixture. When the piston reaches the top of this stroke, the intake
Now
valve
it's going to come back around, right? And then it just continues, right? This is the way we are allowed, this is the way that we,
strokes of the piston to create one.
this is the way that we can take linear motion, right? This is linear motion, straight up and down. We are taking linear motion and converting it to circular motion, right? That's a big achievement that we came up with at some point, right? To be able to take something that goes and moves back and forth and somehow convert that into turning something. And that's how we can turn the transmission, which turns your wheels and everything else, right? But all it's based upon is this diagram of a piston, a rod, and then this. I'm going to show you another short video. This one is an actual, like, real model of one working. No, it's a model. It's not really blowing up gas, but you know, this light flashing is the spark. It blows up, and this cycle happens, and it happens very fast, as you can see. So as this goes up and down, this is turning, right? Yeah, so when you look at your car and it has this thing, I think it's called a tachometer, it reads what's called your RPMs, it's your revolutions per minute. It's telling you how fast this is spinning, how many revolutions it makes in 1 minute, right? So you step on the gas, right, and it spins faster. And then that spinning motion goes to your transmission, and depending on what gear you're in, that will determine what the speed of your vehicle is. But your engine is always going to be based upon how much gas you're pushing into it, and that will either speed this up or slow this down. All right? Got a basic idea of what the picture is? Yes? Or like the motion here? All right, what we're going to do is we're going to do a problem where I'm going to give you this same sort of diagram, and I'm going to tell you how fast this piston's moving down, and then you're going to tell me how fast it's spinning at an instant in time. Because what happens here is when it comes up, right, when the piston comes up, it actually has to slow down to get to the top, and then stop, and then it has to come back down. So it speeds up and then slows down again and then comes back up. So while the piston's moving, it's not a constant speed, right? It's not a constant speed because it goes up, slows down, speeds up, changes, right? So we can't just say that it's constant. So there's some relationship between the piston and how fast it's moving at an instant and how fast our crank is turning at an instant. So here's a problem that I gave another class, and we're just going to do this problem. Now, I messed up some of the wording, but so here's what I say here. First, some terminology. This is our piston. This is our